So here's chapter 3. We're going to talk about concurrent objects. We've got our 3 little processors working on memory, and in memory we have 2 objects, and they sort of overlap. And the red processor works on an object by itself, whereas the blue and yellow work on the same object. So the question is, what is a concurrent object? How do we describe it? How do we implement it? How do we know if we did it right? So let's take a Fifo Queue as an example object. So we have an enqueue method, and we have a dequeue method. And we could make a lock-based queue something like this, where we have a head and a tail pointer, and we have items, and we have a lock. And the idea is we're going to pretend this array of items goes in a circle, and we're going to use that lock to access things. So this is the constructor, and initially we're going to set the head equal to the tail equal to 0. And we're going to instantiate the lock and instantiate the array. So here we're going to show how to do the dequeue method. We're not going to show you how to do the enqueue method, at least not in the slides. And so, but remember the picture, right? When we enqueue a method, what do we increment? What do we move when we're enqueuing? Well, let's look at the dequeue method. So in the dequeue method, what we're doing, we're saying if the tail is equal to head, then the thing is empty, right? And if but otherwise, what we're going to do is we're going to get head percent items dot length. So the percent operator is of course the modulus. And what I can do is, no matter how big the head gets, right, if I perform the modulus with items.length, it maps it back onto the array. So this is the way we build the concept of the circle in. So we can keep incrementing head, and it will just essentially walk from the first element to the last and then back to the first because of this modulus operator. So if we're taking things, if taking things off the queue increments the head, how are we going to put things on? How are we going to enqueue them?
Incrementing the tail.
That's correct. We're going to increment the tail to put things on there. Okay, so hopefully that part is obvious. Any questions on this?
Makes sense.
All right. So I've already sort of described this, but there it is, highlighting the steps. Okay, and that's our dequeue method. And it should be correct because the modifications are mutually exclusive. Now we can have the same implementation without mutual exclusion. For simplicity, only 2 threads. One thread enqueues only, the other thread dequeues only. And it can look like this. We set our head and tail and items. And when we enqueue an item, first we put it into the array, and then we increment the tail. And you know, there's a question, how do we define correct when modifications are not mutually exclusive? But the idea behind this particular wait-free 2-thread queue is that if I try to enqueue the method, I don't need to lock anything because the other thread can't see what I put on there until I increment tail. And only one thread increments tail and only one thread increments head. And as long as we've got 2 threads like this, we actually don't need the synchronization. So that's kind of a useful optimized case to know about. So what we need is a way to specify a concurrent queue object. We need a way to prove that its algorithm implements the object specification. So let's talk about those things. We have correctness in progress. So in a concurrent setting, we need to specify both safety and liveness properties of an object. We need a way to define when an implementation is correct and the conditions under which it guarantees progress. So let's begin with correctness. If precondition, the object is such and such a state before you call the method, then postcondition, the method will return a particular value or throw a particular exception, and postcondition continued, the object will be in some other state when the object returns. Okay, so you can make specifications of this type. Pre and post conditions for the D queue would look like this. So we have a precondition, the queue is empty. A post condition, we return the first item in the queue is non-empty. The post condition is that we return the first item in the queue, and an additional post condition that we remove the first item in the queue. Okay, so the middle one describes the return and or exception. The last one describes the state change. Welcome, Derek. Welcome, Sarites.
Sorry, my volume was too low. Did you say something?
I just said welcome.
Oh, okay.
I'm just welcome, Sarites.
Okay. Thanks.
All right, so I'm just gonna so we're discussing how we know whether a concurrent object specification is correct. And what we've done is we've said we have a precondition, the state that the object is in beforehand. We have a then post condition, which is the return value or the exception that the object will return, and the post condition, which is what the state change is for the object. And we were talking about a Fifo queue. So we're going to have a precondition that the queue is not empty, a post condition that the first item is returned, and a post condition that the state change, that is the first item, is removed. We can also have a precondition. We can also describe this scenario. Either the queue is empty, we throw an empty exception, and the queue state is unchanged. So both of those work. So these are what are called sequential specifications, and the interactions among methods are captured by side effects on the object state, and the state is meaningful between method calls. And the documentation size is linear in the number of methods, so we just have to describe each method by itself. And we can add new methods without changing the descriptions of the old methods, which is great, right? But what about concurrent objects? What about concurrent specifications? The methods, if we add a new one, do we change the other ones? And the documentation, is it still linear? And if we add new methods, what does that impact? So the first observation is that methods take time. When I go to enqueue something, the method call spans some number of microseconds or nanoseconds, who knows what. And so we might have, in this example, it takes a full second for this method call. What we're going to do is we're going to first call the enqueue method, and then it's going to return void. Okay, and in between that, it's changing the state and doing things. So sequential methods take time. Who knew? And you don't necessarily think about that maybe, but they do. Concurrent methods, a method call is not an event. It's an interval. It takes place over a span of time, and state change occurs during that time. So concurrent methods might be overlapping. So we have a method call begin and another method call overlap with it, and maybe a third method call overlap with the second one. Each method, if we want to use sequential descriptions, then we can describe each method in isolation. If we want to handle concurrent situations, we must characterize all possible interactions with concurrent calls. What happens if two overlap? What happens if there are two D queues, an N queue and a D queue, two N queues, and so on? In sequential, we can add new methods without affecting older methods. But in concurrent, everything can potentially interact with everything else. Panic. So what does it mean for a concurrent object to be correct? What is a concurrent Fifo queue? FIFO means strict temporal order. Concurrent means ambiguous temporal order. So let's look at our DQ method. We lock, and all modifications are done using this mutually exclusive semantic, right? So intuitively, what happens is we have a region where everything is locking. Then we have a region where the actual state change occurs, and then we have a region where the unlock occurs. So this larger method call is made up of these parts. And the part where the state is actually changing, in this case, the orange and the green arrows in the middle, these do not overlap. That's what we're trying to achieve with this. So there's the NQ and there's the actual DQ happening. Okay, and those don't overlap. And so we can regard the behavior as being sequential. And so let's try to capture the idea of describing concurrent via the sequential. So each method should take effect, and this is going to be called linearizability. So each method should take effect apparently instantaneously between the invocation and response events. And we say the object is correct if this sequential behavior is correct. And any such concurrent object is linearizable. So this is the way, one of the ways we are going to try and solve the problem of concurrent objects is we're going to describe objects that are linearizable. So as an example, we have an NQ method, an NQ call and another NQ call, and then a DQ, and then another DQ, okay? So the way this has to happen is we have to NQ the X, NQ the Y, and that way we can DQ the X and DQ the Y because we have to DQ in the same order that we NQ. So if we choose these lines, then everything is linearizable and correct. Now, I could have chosen to draw the lines this way. I could have chosen to draw the lines this way, but if things happen this way, then the execution isn't correct because I NQ'd Y and NQ'd X, then I DQ'd X and DQ'd Y. The system wouldn't be behaving properly. So let's think again. We're going to put some more methods on, more of these NQ calls and DQ calls. So, you know, if we have the NQ method and we pick these instants in time where we say the method takes effect, that means that this is the latest time this one can take effect, and this is the earliest time that this one can take effect. If I put the markers here as they are now, if I use this starting point for the NQX and this starting point for the NQY, is my execution consistent? Okay, so let's say that this NQ method takes place, we take this as our linearization point for the NQX, and we take this as our linearization point. Oh, shoot, I didn't mean to click on it. And we take this as our linearization point for our NQY. Okay, so the question is this linearizable? Can I choose a linearization point for my Q.DQ method such that this execution makes sense?
So you're DQing Y while you're NQing Y?
Those two things are overlapping, but okay, so what we're doing, let me just back up and describe it again. Okay. You really need to stop me if you don't understand what I'm saying. So we're talking about a thing called linearizability. We're trying to view this as if each object takes effect instantaneously somewhere between the invocation and the response when the method is called and when it finishes. Okay, and the object is correct if this sequential behavior is correct. Okay, so in this case, this first case, right, we have these methods, right, and the there's the red thread and the blue thread. And we have the red thread is enqueuing X and enqueuing Y, or the red thread is enqueuing Y and dequeuing X, and the blue thread is enqueuing X and dequeuing Y. Now, if only one of these threads were happening, right, it wouldn't make any sense. I can't enqueue X and dequeue Y, right? I need for dequeue to come after enqueue, right?
Yeah, that makes sense.
Okay, so what's going to happen next? We're going to choose these linearization points, and if we choose them like this, if we put this line here, and this line here for the blue thread, and this line here and this line here for the red thread, then it all makes sense because we enqueue the X, we enqueue the Y, we do dequeue the X, then we dequeue the Y. Okay, and that's linearizable. Now, if we had chosen different linearization points, this would represent an invalid execution, right? Because I enqueued Y before I enqueued X, but I dequeued X before I dequeued Y. That doesn't make sense, right? It's a FIFO queue, right? It's a FIFO queue. So this is not a valid choice for the linearization points. The first one was. Okay, so now we're doing it again. We've got these methods, right? And we could choose linearization points like this. If we wanted to be extreme about it, we could choose the linearization points such that this blue one is at the end of the enqueue method, and this red one is at the beginning of the enqueuy method. So these are possibilities. Now, if I choose these two linearization points, will the execution be correct?
No, because X would have to leave first, right?
Right, because no matter what I do now, because I put this NQY here, I mean, this NQX has got to come first, right? So we can't DQ it. All right, so here's another example where we're going to start the NQ method, and then the method doesn't finish in the time that we're looking at. It just, as far as we know, it takes forever. And then we have a DQ method that happens here. Now, is this linearizable?
I guess as long as
Yes.
the blue one starts first.
Yeah. So we could pick that, for example. All right, here's another one. So what about this one? Is it linearizable?
No, because X would have to leave first.
Well, anybody else have a different opinion?
I would say yes, as long as DQY somewhere executes after DQX.
Okay. All right. So let's take a look at what happens. Now, if we choose these as our linearization points, we NQY, then we NQX, then we DQY, then we DQX, we have something that is linearizable. But on the other hand, and in the other hand, we could choose NQX, NQY, right? Then DQX and DQY, and that's also linearizable. So there's two different ways that we could make this work. And multiple orders are okay, but the point is, regardless, it's linearizable. Does that make sense? Does it not make sense?
Yeah, so, oh, go ahead.
No, I wasn't saying anything.
Okay, well, I was just going to say, so basically, the green arrows, they can look like they're out of order, but as long as the execution point, the tick mark, lines up in a way that makes sense for a FIFO queue, then it's linearizable. Yeah,
so actually what we're going to do, right? I mean, the green arrows just give you a span, a partial order for things.
Mm-hmm.
And what we're going to ask ourselves, can we put linearization points on those green arrows in such a way that it makes sense. All right, just leave the green arrows as they are and see, is there a place where we can draw a red and blue line such that this all works? And if it is, it's in principle linearizable. So here's another example. Read-write registers, okay? So we've got a bunch of different activities going on here. Is this linearizable?
You can't read and write at the same time, right? So
well, but again, what we're going to do is we're going to draw lines on these inside these arrows and pick that as a linearization point. Okay.
So those lines, just to clarify, like that's the whole method, just one little tick of time. It's not like it starts there and ends, you know, somewhere else.
What we're doing, right, is we're pretending that we can pick a point in time where the state changes, right? So what we want is, even though the method is going to take time, in principle, as far as the outside world goes, the state changes in an instant somewhere during that method call.
Okay.
And
that makes sense.
We're trying to say, is there a place where that state change could occur such that this execution would be consistent? So this this read one here has to happen after a write one. So that means that the write one has to happen before this point, right? You see what I'm saying?
Yeah.
So if the read one is going to happen at the latest possible moment, that means the write one had to happen before it. So I would have to draw this line maybe over here somewhere. So the question is this execution consistent? Is it linearizable? Is there a way to draw lines such that it works?
Yes.
Okay, so where would you, well, I can't, it's kind of hard for me to ask you to draw the lines because you can't, can you draw on the screen?
I don't think so.
I think you can.
I think you have annotations turned off.
Do I?
Yeah, there's an
I think
annotate
so.
button. I see it.
Wonder where that would be.
Somewhere in your Zoom settings. I don't remember exactly
Annotate.
where.
And okay, so I have an annotate button myself. But you don't have that, huh?
We do on view options for your screen, but it doesn't look like I can actually draw on it. Like there's like a palette of things I can use.
Right.
But yeah, I don't see a way where to actually draw onto.
So let's see if I can draw. I'm going to just try it. So let's say I pick this as my point for 0. Okay. And now I'm going to pick, I guess, the latest possible one for read. I could pick something different, I guess. But write has to happen before that, right? So this write 1 has to happen here. Then I don't know when I want this write 2 to happen, but now I've got to read a 0. Is there any way I can make that work?
It can be at any time, right? Because 0 was already written.
Well, 0 was written back here, but after I write a 1, it's no longer a 0, so I can't read.
This is still a queue, or well,
this is not a queue.
Only one value per.
This is a memory register.
Ah, okay. Yeah, there's no way.
Right, there's no way. So this is what I told you before. The write already happened by the point of that dotted line, and so the write has to occur there, roughly, or something like that. And the question is, can the read 0 be made to be correct? And the answer is no, right? So this is not linearizable. Okay, so what about a read 1? Can we get a read 1 to occur? And I changed this last one to a read 1. Can we get this to work?
Nope, because write 2 will execute before read 1 does.
Well, okay, so in theory, right, you're right, but in theory, I could say write 2 happened here and write 1 happened there, and then this read 1 would work. The problem is, I also have a read 1 here. And this read one here constrains the right one to happen on or before this dotted line. So this isn't okay, right? I can't do this one. So I'm forced to put it back. I'm forced to put it back here, right? And so this isn't consistent. Okay, so that's not linearizable either. Now is it linear? Now what about this? Is this linearizable?
Yes.
Right, because I can draw a line here. I can draw a line here. I can draw a line here. And I can draw a line here. And that should all work, right?
Looks like it.
Ta-da! Linearizable. Okay, so we're going to split everything into events, into two events, right? We have the invocation, which has the object and the method and the arguments, and then we have the response, which is going to be usually you know, the return type, okay, or the exception, row is empty, right? So in this case, we're going to have thread A, method NQ, object Q, arguments X. Okay, and here we're going to have a sequence of invocations and responses that looks something like this, right? And we're going to look for matches. So we're going to say that if the object names agree and the threads agree, then we have a match, and that's a complete method call. So that's a history, and in that history, we've got those two complete method calls, the NQ3 and the DQ3. I'm sorry, that's the history on Q. So if I just look at the object Q, right, then I have that history. And if I just look at thread B, then I have that history, right? So that I can sort of slice it there with that pipe symbol. And so there are various sequential histories, and I can have a match, another match, and another match, right? And then a final pending invocation, we're going to say that's okay for a sequential history. So method calls of different threads are not interleaving here. But this one is different, right? So if I look at this, I've got this NQ and this finish happening here, and then this other stuff happening in the middle. And if I look at the per thread projection, if I look at B sees NQ4 and then void, and DQ and then 3. Okay, so that's the per thread projection, and then we can get a per thread A projection that just NQs 3 on Q. And we have two histories are equivalent if threads see the same thing. So these histories, I mean, if things happened in one way or the other, it doesn't matter. They're equivalent because the threads saw them the same. So a sequential multi-object history is legal if, for every object X, HX is the sequential specification for X. So in this case, we want to say a method call precedes another if the response event precedes the invocation event. So if the response precedes the invocation, right, then this method is before this method. And if that's not true, right, then the methods are probably overlapping in some way. So this green method here overlaps with this, with this brown method or orange method. Okay, so given a history M, method executions M0 and M1 in history H, we say that M0 precedes M1 if M0 precedes, if M0 in the history, if M0 precedes M1. So the relation M0, M1H is a partial order, and it's a total order if H is sequential. A history is linearizable if it can be extended to G by appending 0 or more responses to pending invocations and discarding other pending invocations, so that G is equivalent to a legal sequential history S, where the G is an S. Okay, so this is all a very complicated way of saying things. And what we have is we have this history. Given this G, we want to be able to see what we can choose for an S. Okay, that's equivalent. Okay, so the actual the limitation is here on what we can have for S, not on G. It's saying that you can't just pick any S, right? You have to have an S that contains this arrow G that has these two relations, that has to have A before C and B before C. Okay, and what this is choosing is that B happens before C. It's choosing this linearization point such that this happens, right? So that's the way we're making this work. So some pending invocations took effect, so we keep them and we discard the rest. And so the condition arrow G and arrow S means that S respects a real-time order of G. And here's an example. So we've got, we're going to complete this pending invocation by adding a Q void. And we're going to discard this other one that starts with a Q, NQ of 6, right? And then we've got this execution, which is complete. And this is an equivalent sequential history that we can construct from that. Okay, so we NQ4, we NQ3, we DQ4. And that all looks like this down here. So a history H is linearizable if and only if for every object X, H of X is linearizable. We care about the objects only. Okay. It's a powerful specification tool for shared objects. It allows us to capture the notion of objects being atomic, that is happening at one point in time. So don't leave home without it. Now, a sequential history, a sequentially consistent execution, on the other hand, is a more complicated beast. A history is sequentially consistent if it could be extended to G by appending 0 or more responses to pending invocations, discarding others, and it's done so that G is equivalent to a legal sequential history S. What we don't have is this other statement here. So what does this mean? We don't need to preserve real-time order. We cannot reorder operations done by the same thread, but we can reorder non-overlapping operations done by different threads. Okay, and this is often used to describe multiprocessor memory architectures. So this is all kind of confusing, and I'm sorry about that, but let's try to make it clearer with some pictures. So here we have our friend that we had before, where we said something was not linearizable, right? This all looks familiar. But what sequential consistency says is before we draw these lines, we're allowed to move these things around. So I'm allowed to move these events outside their little arrows here now. And I can pick these points just so long as I don't, for example, I can't make Q.NQX happen after Q.DQY. Those two things have to stay the same order. But I can put this other one, I can move things around however I want, so long as I don't mess up a single threads. So this is sequentially consistent. Does that make sense? Does anybody have a problem?
So can you explain again why you're able to move the tick outside of the arrow, kind of like before?
Because this is a definition of a new kind of consistency model, right? And my definition says that the only thing I have to preserve, right, is the order that one thread sees. So the only thing I have to preserve is that QNQX happens before Q.DQY. It doesn't matter, right, if I want to take this one and move it way early or way late, or if I want to take this one and slide it way over here and this one and slide it way over here, right? I can do those things. The thing that I can't do is I can't change the order of these two things, right? I can change the order of these two things, and I can change the order of these two things, but I can't change because those are on different threads, right? But I can't change the relative order of those two. And I see. So that's the rule that I'm dealing with. And so long as I respect that rule, I can say that something is sequentially consistent. And this is a weaker consistency than linearizable, right? So, and this is something that people use to describe multiprocessor architectures, is sequentially consistent. And so, but here's a problem, okay? Sequential consistency is not a local property. So we thus lose composability. So we can have objects be sequential. We can have sequentially consistent objects, but a whole execution that doesn't quite make sense. So what do I mean by that? So I have a history that looks like this. Okay, and I want H over P to be sequentially consistent. So I can move things around like this to have things consistent for object P, right? That's consistent. And I can make H, the history over Q sequentially consistent. So I just look at the Q's, right? And I can make that work. But what I can't do is take these two orderings and make them work together, right? They aren't compatible. And sometimes you may have heard, if you dig around on various websites and study obscure things like memory models, you may have heard, you know, that the Java memory model, the original one, allowed for time travel or something. And that's the kind of thing that you've got here. You can't tell what happened first. And part of what goes on with this, and part of what the people who are, you know, making the guts of the computer work is, if you're looking at optimizing a thread, for example, you can say that this NQX and this NQX here, because they're on different objects, really, they don't affect each other. So you could do them in the opposite order if the compiler thought that would be faster for some reason. Okay, and the compiler will reorder things like this, and there are special instructions that you can give it to tell it not to do that for parallel codes. But in general, this is a problem that you might deal with, right? Your machine is only looking at a sequential consistency. So we've got this kind of crazy ordering of things that we can look at individual objects and they work, but they don't work if we look at the whole execution. And real world hardware memory is often even weaker than sequential consistency. And it turns out it's just hard to get even that to work. So linearizability is more appropriate for high-level software design, which is more likely what you all would be doing. Okay, so that's the end of the notes. And before I go on to other things, I want to hear questions. So, all right, since nobody has any questions about any of that, we will move on. All right, so what I'm going to do now is I'm going to show you some other things. Let's say, okay. So, is this execution linearizable?
Yes.
So,
Oh wait, there's a DQ at the beginning. No.
anybody else? Everybody agree? Anybody disagree?
I would say yes.
I would agree also.
Same.
Okay, so let's look at this DQX. How can we make this valid? DQX has to be preceded by what?
NQ1.
So is there any way I can draw a line here so that it will be before this line? Before this event? A line here and a line here? The answer is no, right? I'm NQing on the same thread after, so it can't work. So the answer turns out in this case to be no. However, what I'm going to tell you about now is a third kind of memory consistency. And the way this works is I look for gaps. So there is a gap here where nothing is executing. And I guess there's a gap at the beginning, you could say, and a gap at the end. Nothing is executing inside these blocks, right? Right?
Yep.
Yeah.
Hold on. Okay. Where'd my whiteboard go? There it is. Okay. So the point is, so long as I don't move things across these blocks, I'm allowed to reorder them however I want in a thing called quiescent consistency. So that means that I can take this, right? I can take this event and can I choose a color? So in any event, what I can do is I can make this event happen first, and then I can make this event happen second, and then I can make this event happen third. And I can pick this ordering because these things are all part of an overlapping execution. Okay? All these things overlap. And so I can reorder them. And this one I can't reorder with anything because it's by itself. I can't move anything across the gap. But as so long as I don't move things across the gap, I can reorder. Does that make sense?
Yes.
Yes, it does.
All right, so that's our concept called quiescent consistency. Now I'm going to take you to, I guess, some old exams, because that's where I've got this stuff more or less written. All right, so let's take a look at this. Okay, so let's look at this question 2. So what we've got are these executions, and they have to happen in the order that the events have to happen in the order of the numbers. So 1 has to happen before 2, has to happen before 3. It's just, I guess, a little simpler way of, you know, saying what the methods are. So, I mean, so maybe in this case, the operations are all increments that return that value. So initially the thing is 0, you increment it the first time, it's 1, you increment it the second time, it's 2, you increment it the third time, it's 3. Okay, so for each of these, A, B, C, and D, I want you to figure out whether the executions are linearizable, quiescently consistent, or sequentially consistent, or some combination. All right, so let's start with A. Let's see what you can do.
Is this still in terms of reading and writing, or enqueuing and dequeuing?
Okay, so no. What I said was, you're to think of this as an increment operation, and this number as the result that you get back. So initially you have a register with value 0. You increment it the first time, you get a 1. You increment it the second time, you get a 2, and you get it a third time, and you get it a 3. Okay, so that's the operation being described here. So these things have to happen in the order they're numbered. Does that make sense?
Yep.
So who can tell me if this first execution is linearizable?
Looks like it is.
I would say so, yeah.
I would also say it's linearizable.
Correct. So I could draw, say, here, here, and here, and it all works. Now, here's one of the qualities of linearizable. If something is linearizable, it turns out that the other two things will automatically be true. So if something is linearizable, it will also be sequentially consistent, and it will also be quiescently consistent, because linearizable is the strongest quality, right? These other two things, quiescent and sequential, allow you to do additional reordering of the method beyond what these time limits allow. But linearizable requires you to stay within them. Okay, so if you get this first one, then the other two automatically work. Does it make sense?
Yep.
Okay, now let's look at B. Think about B. Is it linearizable?
No.
Does everybody agree?
Yeah, because 3 can't come before 4.
3 can't come before 4. There's just no way. What about sequentially consistent?
Yes.
How does that work?
Isn't that the one where you can choose the start of 3 to be like beyond what shows? Like if you draw the line before 3 for when 3 executes.
Right. So what you're saying is I want to choose this and this, right? Where this connects here.
Yeah.
And then this and this. And yes, this is sequentially consistent. That's correct. Is it quiescently consistent?
No.
Right. Because in quiescently consistent says I can reorder these events among each other. I could say 4, then 2, then 1, but whatever I do, I can't get 3 to go before 4. So this one is sequentially consistent. So this one is linearizable. This one is sequentially consistent. What about C? Is it linearizable?
No, I would say it's not.
No.
So it's not, because there's nowhere I can draw these lines such that one will come first, right? No matter where I draw this, something else has happened before one. Is it sequentially consistent?
No, because 1 comes after 3 on the thread B.
Correct. Yeah, it just can't work. However, when I'm looking at quiescent consistency, right, I'm allowed, I just love this annotation. I'm allowed to take this set of things and reorder them. So I can switch the order of these two. And then I can have 2 in the middle, and it's quiescently consistent. So that's Q. Now, what about this last one? Is it linearizable?
Nope.
Is it sequential?
No.
Is it quiescent?
Nope.
So it's nothing.
Can you explain why that's not quiescent? I guess I'm just a little confused on that one concept.
Well, so quiescent allows me to reorder 1 and 4 because they overlap. And I can reorder 2 and 3 because they overlap. But I can't move anything across the gap.
Oh, that's right.
Hopefully we used a different set of lines in this year. Okay, yeah, here's another. I don't like that one. That's not the one I want. Okay, this is the one I want. All right. Let's look. Whoops. Let's look at this execution. Is it linearizable?
Yes. No. Because of DQ at the beginning.
Yes, correct. Is it sequential?
No.
No, it's not.
Is it quiescent?
Yes. Because there's only one section and you can just move them all around.
There are no gaps. I can reorder everything however I like. What about this one? Is it linearizable?
No.
No.
Is it sequential?
Not sure.
Well, you understand how sequential works, right?
Yeah, I guess I'm just confused with the like, is NQ2 allowed to come before NQ1? Like, does
Well, it's a FIFO queue. So if I NQ1, then and if I NQ1 and then if I NQ2 first, then I have to DQ 2 first. If I NQ1 first, then I have to DQ1 first, right? It has to be consistent with the behavior of a FIFO queue. So is there a way to make this sequentially consistent?
I would say no.
Yeah, that's
Right.
what I'm thinking.
What about quiescent consistency?
No, because NQ or Q NQ1 would have to be first, and you can't move it since there's a gap.
What about this one? Is it linearizable?
Yes.
I'm gonna say no.
Okay. Anybody else have an opinion? So what I can do, I can say this happens here, this happens here, when this happens here. NQ1, NQ2, DQ1, consistent. Okay.
Oh, I see. I see.
Is it sequentially consistent?
Yes.
Why?
Because if it's linearizable, it has to be both sequentially and quiescently consistent also.
Correct. Now, what about this one? Is it linearizable?
No.
No.
Anybody disagree? What about sequential?
No.
Anybody disagree? Well,
Wait, actually, yes, it is sequential.
so I could take this and slide it down to here, right? I'm going to put the line there. And so I'll pick this happens first, this happens second. And then I'm going to pick this as happening third. this is happening fourth, and this is happening fifth. So NQ3, DQ3, NQ1, NQ2, DQ1. It works, right?
Yes, it does.
But it hurts your head a little.
Just a little bit.
Is it quiescently consistent?
No, because Q.DQ3 is off on its own, and you couldn't move it because there's a gap.
We can't, so the gaps are here and here.
I would say that it is quiescently consistent.
We can reorder any of these guys. So we can pick this as 1, 2,
Oh, that's right.
and 3. So this one is fun because it's sequential and quiescent, but not linearizable. Isn't that fun?
Sure.
All right. Now, you may remember in the last lecture, I talked to you about recursion. And I told you that recursion is good for problems where we want to search a space, okay? And so what I've got here, this is a Python code. I know we normally use Java, but for whatever reason, I wrote this in Python. I hope that you can all read Python. It's not really a difficult language, but what I did is the way I constructed this program is I have an execution which I describe with read x equal 3, write x equal 2. So these are memory registers, and I can potentially have, you know, A through Z of them, right? And I'm not describing the limits on, you know, the beginning and end points of these things, because what I'm going to try to do with this program is determine if the execution is sequentially consistent. And given my freedom for moving events around, I really don't need to know precisely when the start and end are, okay? Does that make sense? Does it not make sense? Somebody should, you know, say something to make me feel better.
I will say, is the screen really blurry for anyone else?
Yeah, it's hard to read the actual code.
Okay,
See,
it's focusing in now. I can start to read it now.
Yeah, it is.
hold on, let me try something. But you had no trouble reading it before, right?
No, it fades in and out sometimes.
Yeah, it started this week. Sometimes the slides would get blurry, but they would focus back in after like a minute.
Okay, well, you need to let me know if you're having trouble seeing stuff. You can't just let me like blabber away.
Well, usually you can kind of make it out, but I guess with the code, it was kind of hard to read since it was smaller.
I'm trying to make the font bigger. All right, let's see. How's that?
It's better.
It's better, yeah.
All right, so up here, I'm describing an execution, and I do that with an array of arrays. So each array represents a thread, okay? And my question is, why is that highlighted? Oh, well. My question is, what can I do to determine if this execution is valid? So one of the things I'm going to do is I have this check method. And the way check is going to work is it's going to go through a sequence of instructions, and it's going to determine whether that represents a valid sequence of instructions. Now, how many of you have never heard of a regular expression? Wow, everybody has heard of regular expressions. Great. Okay, so in this case, what we're going to do is, because each of these things are strings, all right, we're going to use a regular expression to parse them. And the regular expression says that the first thing in the string has to be an R or a W. And we want to capture that, use a parentheses to say we want to capture that in group 1. The next thing is going to be a colon, and then the next thing is going to be a letter from A to Z, followed by an equal sign, and \D is a number, is a digit, and \D plus is one or more digits. So this is saying that I have read write followed by colon, followed by letter, followed by equal, followed by a number. Okay, and this loops over each of the instructions in the list, parses it with the regular expression, extracts the read write letter, extracts the variable name, in this case, so this would be W would be read write, and X would be var, and value would be 2. So it gets those three things: the read write, the variable name, and the value. And then if the read write is equal to W, that means it's writing. So we've got a dictionary here called state. And what we're going to do is we're going to set the value of that variable equal to that value. Now, if it's not a write, then it's going to be a read. So we're going to say if that variable is not yet defined, it's not in the state, or if the state variable does not equal the value, then we return false, and this execution is not valid. Okay? Does that make sense to people?
Yes.
Anybody have trouble with this? Need something explained again? So, right, does this make sense to you?
Yeah.
Brandon, does this make sense to you?
Yes.
Chris?
It does.
Good. Okay. So now we're going to have our main method, which is our isSeq1. Let's actually go down to the bottom. So this is our method that says is sequentially consistent. And what I'm going to do is I'm going to create an array. Well, I'm going to call this isSeq1 from isSeq. And isSeq1 is going to take the execution, and then it's going to take another array, which is going to have a 0 for each thread in the execution. And then it's going to have an empty array. All right. And what it's going to do, make this a little bigger. What this is going to do is it's going to go through, it's going to iterate over the length of the steps array. And the length of the steps array should be the length of the execution array. Those should be the same. It's the number of threads that we have. Okay. And then for each thread, we're going to ask if the current step, the center array, which I initialized to all zeros, that's which instruction is going to execute next on that thread. So they all start at 0. So we're going to say that there are more executions, there are more things to execute if steps I is less than len exec I. So if these are all the instructions that the thread has to process, and this is the next one it's going to process. So as long as this is less than this, we have more to do on that thread. We're going to set this done equal false here just to signify that at least one of the threads in this set of threads is not done. And you know what? I'm going to make this a little clearer. I'm going to say num threads equal len steps. And I think that makes it a little clearer. All right. And then what I'm going to do is I'm going to create a new set of instructions. Now, our current set of instructions is this last argument, and this starts as an empty array. And what I'm going to do is I'm going to say our next instruction is our current list of instructions plus a new one, which says the instruction add exec I, step number steps I, and that will give us the string from the table above. And then we're going to append another little string that says which thread it is that's executing. Okay? And then what we're going to do is we're going to check to see if this order of instructions makes sense. If it does, we're going to increment the steps counter and recursively call isSeq1 again. And we're going to call it with inst2, okay? And then after it's finished, we're going to put the steps back. So this is modifying the state and putting it back around each of these calls. And by doing this, I'm going to search all possible orderings of instructions on each thread. Okay, does that make sense?
Yeah,
It does.
All right, so then I have two things that I can do. I can either print all solutions as I find them, or I can return an answer when I find it. And we can run it in either mode. Okay, so when I'm running it this way, it's finding one valid answer for the sequential consistency. So the first one is we're going to say we're going to write x by 2 with thread 2 is going to write x equal to 2. So this instruction is first. This instruction here corresponds to thread 1 executing this. This is thread 0 executing this. Okay, and then thread 2 executes. Thread 0 executes this, and then thread 1 executes this. So the order is this, 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 this. Okay? And that's consistent, and it found it. Now, this would be all possible executions that make sense, and we can walk through each one to make sure that it does. So write x equal 3, read x equal 3, write x equal 2, read x equal 2, write x equal 2. Okay, so you can look down all of these things and make sure they all make sense. But these are all valid executions, all possible ways that this could be executed sequentially. All right, does this all make sense?
Yes.
So I'm going to give you guys this program, and you can plug in various executions into here for however many threads you want, with however many steps you want. And you should be able to determine whether the execution makes sense. Okay, and this could be a little tool that you can use to figure that kind of thing out. Now, what would be nice to have is something that allowed you to do linearizable or quiescently consistent executions. And in some fashion, I'm going to try to figure out a way to set that up for you as a homework problem. But in the meantime, you've got this that you can use to explore whether you think something is sequentially consistent or not. Does anybody have any questions on anything? All right. That's it for today. I will see you all another time.